Okay, let's continue on with problem 5.90. If you remember correctly, we finished last time by calculating the contribution due to work, or the shaft work contributed by the flow crossing the inlet boundary, which in our case was boundary 1. And now we're going to calculate the portion due to boundary 2, the outlet. So we have our outlet. Here we know that the relative flow W is coming out at 120 degrees from tangential, and we know everything else about the geometry of the flow. So this one is a pretty straightforward application of doing our integrals for torque. But just to be clear, we're going to draw some vector triangles here. And so here's our outlet. And r hat still points outward, and theta hat still points in the counterclockwise direction. And we can draw some vector triangles. So we know that W hat, that W coming out, that this angle here is 120 degrees. I'm just going to write this one here being 60 degrees. We know that U is going this way because our device is spinning in a clockwise direction. And so we know that V, which is U plus W, is going to be somewhere, well, that's not a particularly good drawing now, is it? It's going to be somewhere like this. We know that the volumetric flow rate, when we do the integral over the area, is going to be equal to 2 pi r2, the radius, b, the thickness, times minus WR. And I write this as a minus because WR is in the negative r hat direction. Sorry, W is in the negative r hat direction. And so WR is going to be a negative number. And we always want Q to be a positive number when we do these problems. So that means that WR is equal to minus Q over 2 pi R2B, which from before was, let's see, 20 cubic feet per second. Divide that by 2, divide that by pi. R2 is 2 feet, so we divide by that. And B was, what was it? It was about 0.08 something or other. So let me see here. I think I have it stored. Whoops, no, I don't have it stored there. Yes, I did have it stored there. So I get, sorry about that, I get minus 19.30 feet per second. Well, we could have done that without doing all the math, because we know that because the radius is half the radius of the inlet, we could have just taken WR at the inlet and doubled it to get minus 19.3 feet per second. Well, it's a nice check on our calculator math, at least. We know that that is also equal to VR in this case. We can find W theta by noting that, let's see, sine of 60 degrees is going to be equal to minus WR over W. And cosine of 60 degrees is going to be equal to minus W theta over W. And so that means that tangent of 60 is going to be equal to WR over W theta. So W theta is going to be equal to WR over tangent 60, which I get to be minus 11.14 feet per second. So we can find V theta is equal to U theta plus W theta. Oh, my bad. I made one little mistake here, which is that W theta as drawn is in the positive theta direction. This is the whole point of keeping our, being careful with our vectors and what direction things are pointing. So this gets a negative sign here, and this gets a positive sign here. So U theta is in the negative theta hat direction, so it's going to be minus 2 pi 50 RPM divided by 60 seconds in a minute times 2 feet, which is the radius of the outlet, plus 11.14 feet per second. And so I get, let's see, 2 times pi times 50 divided by 60 times another 2 is equal to, oh, look at this, minus 10.47 feet per second plus 11.14 feet per second is going to be equal to 0.67 feet per second. Well, this might work out in the end. Whew. Okay, so we know V theta, we know U theta, we know Q, we know the density. All we have to do is make sure that we keep track of our dot products. So remember, when we do this integral, if we get rho r cross v, v dotted with n hat dA. So this is going to be equal to, let's see, rho times r cross v is just going to be r2 r hat cross v theta theta hat. So it's going to give us a z hat out of that. So that's going to be r2 v theta 2. And we get our z hat there. And then v dotted with n hat. Well, v, we're going to get the r component of v. So we're going to get a VR out of that. And n hat is pointing in the minus r direction. So when we dot those together, we're going to get a minus 1 out of that. The work at 2. Wait, before we do the work at 2, let's get Q in here, right? So we see that wait, rho r, oh, I forgot the whole area. So we get rho times 2 pi r2, that gives us the circumference times b. So that gives us the cross-sectional area of our control surface. So let's see, VR is a negative number, and we want Q to be, and Q is always a positive number, so all of this together here is going to be equal to Q. And we have our rho, and we have R2 V theta 2. And the work at 2 is going to be the torque at 2, the torque due to part 2, which is there, dotted with omega. But omega is going to be equal to, well, excuse me. So we'll write this as, oh, I forgot my z hat as well. It's getting late. I'm getting tired. So we get this as rho Q R2 V theta 2. Omega is just omega the scalar z hat, so we dot that together and we get an omega here. But R2 omega is equal to u theta, so we get rho Q u theta, I'll put 2 on it, times v theta 2. And that's going to be equal to 1.94 slugs per cubic foot times 20 cubic feet per second times u theta 2, which we just said up here was minus 10.47 feet per second, times v theta, which is going to be 0.67 feet per second. Which is, let's see, 1.94 times 20 times 10.47 times 0.67 is going to be, we got a minus there, minus 272 pounds force feet per second. It's getting too late. I don't want to keep track of all of my units. But if we divide that by 550 pounds force per horsepower, then we get, that's all equal to minus 0.49 horsepower. Now this one is not as obvious to say, oh yeah, of course it's negative, because it's such a small number that v theta is nearly radial. We can use our rules of thumb to be sure that this is negative, because at the outlet, if u theta and v theta are in opposite directions, which they are, because u theta is negative and v theta is positive, then we get a negative contribution to the work at the outlet. So the total work of our turbine is the work at 1 plus the work at 2, which is 39.2 horsepower, so or minus 39.2 horsepower minus 0.5 horsepower, which is equal to minus 39.7 horsepower, which is almost exactly what they have in the back of the book, which really just says that our professor should stop doubting himself so much, I guess. Anyway, I don't like the fact that B is only 1 inch wide. That doesn't make good physical sense to me, but the rest of the problem works out, so I guess we shouldn't have been so doubtful of ourselves when we first took a stab at this problem. Hopefully, in walking through and seeing some of the ways that we can easily get tripped up, and seeing some of the ways that we can do some thought experiments to make sure that we're going in the right direction, and even a little self-doubt will help you see the way forward on these problems. To calculate the power is pretty straightforward. Once we had B, to calculate the power was pretty straightforward. You just draw your vector triangles, you keep track of how V and W and U are related to each other, you do your dot products properly and your cross products properly, and the sign convention falls out. You can check it with the rule of thumb that they have in the book, and so forth. The first part, where we were finding B, took a little bit of thought to write down, okay, what do we know? How are we going to get from A to B? But in the end, we were able to reduce the equations down to something that we knew, and even though it was a weird geometrical construct, we were able to figure that out. So in the end, I hope that this has been a good problem for you, and you know, if you have more questions that you either want me to work live or make little videos for you, I'm more than happy to do that. So I will See you next time.